summarize a couple of best practices that you as scientists can, should, must, could adapt to your daily routine when you use software engineering or programming as general to solve your scientific tasks. Alright? And I invite you throughout the course of the whole presentation to just raise your hand if you find something controversial or if you find something you don't understand. Please raise your hand and I'll try to explain it. Alright, so first disclaimer, this is not my work. I simply basically summarize a paper which was published in 2000. Well, it was originally written in 2013, published in 2014, by also the people that came up with material for software carpentry that we have basically covered today. And this paper is open access, and it's called Best Practices for Scientific Computing. And if you want to know more details, maybe even some more references to why the people claim what they claim, I invite you to basically dial over there and download the PDF and then have a read of it. It's a very good paper, I think. Okay, so scientists today. So I think this summarizes, at least from what I've seen, with different variation, the view of a desk of a scientist today, from top. There's the keyboard, mouse, you have maybe some portables, maybe some notebook, but this is how it looks like. Of course it depends from field to field, this is not what it looks like on average, not everyone has Apple or whatever. But something which is undoubtedly a fact, I believe, is that software has become a lab equipment, a piece of the lab equipment. So this statement mostly comes from the biosciences, right, where you really have a wet lab where people go and mix things and everything. But I think it applies to many, many fields. Okay, and I've talked to a lot of people from engineering, from physics, from chemistry, and they would sign this, blindfolded. So scientists spend a lot of time writing software. That is what I mean. I don't mean using software that other people have written or that you bought. This is a given, right? But what I actually refer to is that scientists spend a lot of time writing software today. Most scientists, on top of this, are self-taught. We discussed this extensively over lunch. Typically, they are unaware of what good software is. And basically, what the talk will contain are 24 good practices that you can adapt or at least think about. Because the claim of the paper, this is a little bit provocative, but it's hard to disprove. Good programmers are 10 times more productive than the average. Okay? And I would have to add that there are 10 times more happy as well. And the happy scientist is much better than unhappy one. Okay, let's give it a go. 24 best practices. Rule 1. And this is really the most important rule. When I started, I wouldn't believe this. Right now, after a couple of years, I sign this 100%. You write programs not and never for a computer. You write programs for other people. These other people are your colleagues, your peers, or you yourself. This is what you write a program for. Okay, always keep that in mind. And this refers to the fact that if your code is difficult to understand, this imposes a problem on you, namely that it's hard for you to find bugs and errors. I have one project that I'm working with, is with a rather old developer. He's now a professor at our institute. And you know what he names his variables? A, B, and C. And if this is not enough, it's E, F, and G. So if you read these functions, you have no idea what's going on. Okay? Because it was not, I mean, he's quite old and he understands that, as far as I know at least. He doesn't write for other people, right? He writes the code for his own and he thinks that's fine. And he understands it like this, so I would say, good. Then it's your responsibility. But I would actually urge you to think about what is better to understand. If it's a ratio or a scale, or if it's A or B. You know, for somebody else and your future self, the scale and the ratio are far more easier to digest than A and one appendix to this. This is actually based on scientific fact. And a program should not require its readers to hold more than a handful of facts in their memory over here. And the typical aim is 7 plus 2. There are even editors that force you to limit your functions to 7 lines. I'm dead certain. Okay? Because this is a fact. 7 plus 2 items is the average number of pieces of information that we as humans, on average, can keep in short-term memory. Okay? And 7 is not a lot. Right? So try to keep that in mind. Try to make your functions or your object methods as short as possible. Conversely, and this is a corollary from this, try to break programs into short, readable functions, each taking only a few parameters. I literally saw functions in program code that had no less than 32 arguments. Right? And this is just impossible to understand. Right? Even for users. I mean, this is how we typically start. We go to a course, we learn a language, and then we take the material that we had in the course, and then we say, it's fine, then I'll just add another parameter for my task at hand. And a week later, we do the same, and the same. At some point, we have a 1,000-line function taking 32 parameters. Very hard to actually fix and find problems. 1b, make names consistent and distinctive. Of course, they should be meaningful. And this basically goes back. P doesn't really help the reader's short-term memory. Even if it refers to pressure, P can be anything. Right? Try to be a little bit consistent in terms of the naming, and be careful. Temp can be an abbreviation for temporary or for temperature. But you see, it really depends on your domain, where you basically draw the line. I'm going to skip the IJ thing. Make code style and formatting consistent. Which rules you should follow? I would say I don't care. As long as you actually follow them all through your code, that's the most important thing. And in the 21st century, there's no excuse that this is hard. Because today there are tools to do that, right? And in many IDEs, so in integrated development environments, you can actually set coding styles for different languages. Okay? Yeah, and basically to wrap this up, every inconsistency slows comprehension. Right? So basically this is the motivation. Okay, so let's have a look at automation. This is an assembly line. In the 40s, they were assembling radios back then, and it's trying to symbolize to you the notion of that a computer is there to help you automate things. That's what it was invented for. Okay? And prime rule, let the computer do the work. This is one of the biggest computers we have currently worldwide. This is the Titan at Oak Ridge. Right now, I think top 3 or top 4 in the top 500 listing. It's made to do the heavy lifting. And this also applies to your workstation, let your program. Okay? So let it do the heavy lifting. Make the computer repeat tasks. So write little programs for everything. And this, I mean, literally. When I started with my PhD and started to use a high-performance cluster, I used the command line every day. And I basically then used the history to go back in time and reduce my own commands and all this kind of stuff. At some point, and when your professor actually tells you, could you change this? And by the way, there's also this you can check. This doesn't scale. Okay? So if you have a task that you repeat more than 3 times, this is my personal rule, write a program for it. I mean, that's what these guys were looking for. It's easier to do this with a text-based programming system, and this basically refers to version control. Okay? For systems that actually make you create binary formats like Excel or something like this, this just doesn't work. Okay, save recent commands in a file for reuse. This is basically more like a help for you. So if you remember my three strikes around rule, basically you can combine this. So let's say you work with the terminal and then you see, oh, I repeated this command now more than 3 times. The first step would be to basically copy and paste it to a text file for later usage, and from there on it's very simple to make it to a script, and a script is very easily made into an entire program. So this is more like a suggestion how to approach this. Rule 2C, use a build tool to automate workflows. Who knows what a build tool is? Oh, 4. Oh my god. Who has ever built an open source project? Like, it's not really. Did anybody ever compile something? 1, 2, 3, maybe? I thought you guys were using C++ and Fortran. So, okay, a build tool is something like Make, CMake, the Java people know Maven and Ant. So a tool that helps you to actually take all the source code, compile it into a binary form, and then execute it potentially, or even install it in the system. Okay, and make good use of these. They're here to help you. I just see that the links actually got malformed a little bit. Apologies for this. So GNU-Make would be a viable examples. GNU-Make can not only be used to compile stuff, it can also be used to automate your workflows. Something that is also covered in one of the software carpentry materials. A tool that I recently discovered is NCMEC. I can only recommend it, but I'm not going to go into details right now. Another set of rules, take small steps. We basically had this in the afternoon by using test-driven development, which forces you to take small steps. The actual suggestion in the paper is make incremental changes. This holds basically for programs which have substantial size. Most scientists don't have requirements. This is referring to requirements as a term from software engineering. So typically software engineers, if they start a project, they sit down with the client and then they make, we call it sometimes in German Pflichtenbuch or Pflichtenheft, duty book. And inside this book come the requirements of the software. You can think of this if a bank asks you to write an accounting software, they come to you and say, it must be precise, it must be available 24 hours, it must be in green, it must have Comic Sans MS as the font, all these kind of stuff, right? And it should carry our logo. These are the requirements for the software. And you also, for your own software, have requirements. You want to get the result with method A and the result with method B, and you want to get the result in red as well. Right? So these are the requirements for your software. And typically, scientists are not aware of this. Typically, they just sit down and code, which is okay. But you have to be careful because these requirements force your software into a specific form. If you start out with a very simple algorithm, let's say, and you change it in a very complicated algorithm, your program starts to get slow. By this simple change of the requirement, so meaning that which algorithms you use, you're all of a sudden now forced to think about performance or even to exploit multi-threading. Okay, so multiple cores in a single machine. So these requirements that you as scientists have to your software can have a great impact on how you actually structure your program and what tools you use. So that's why the idea of requirements is actually something to keep in mind. It doesn't have to be something very formal, but just that you have the idea and think about, sit down, look at your program and think, what are the requirements? This also helps you to distinguish what are the pre, the post conditions and the invariants. Because these two, the requirements and these conditions for defensive programming, are highly connected. There's a very tight connection. Okay? Work in small steps with frequent feedback and course correction. Never ever really step into the trap and think that your program is correct. I never do that. And I'm doing this now every day. Okay? I always assume, this goes back to defensive programming, that I commit mistakes. Okay? Very important. On top of this, try to minimize these errors by just following these rules. Never ever, if you sit down, so my personal rule is 30 minutes. If I sit down on a problem longer than 30 minutes, something's wrong. I have to go out. I, at best, should talk to a collaborator. Some people even have a small rubber duck inside on their desktop, and they start talking to their rubber duck and explain the problem that they are just sitting on to the rubber duck. Nobody else than, what's his name, so the founders of C, Königin and Ritchie, I think it was Ritchie that actually started the rubber duck business. So it's not something crazy that I'm talking about. This is really helpful. Explain the problem to a peer or to a rubber duck. So conversely, try to size each burst of work to fit this this 30 minutes or 45 or 90 minutes. It really depends on you yourself. Okay? Right. If you really need longer cycles, then they should be a week or two. Nothing is done within a day. Use a version control system. I have introduced you to Git this morning. Track the changes that you make. Allow them to be undone. Support independent and parallel development depending on the size of your project. This is very essential. And collaborate. Oh, there's a typo, I'm sorry. But the repetition. So collaborate as much as you can, because computers are hairy and complicated beasts. And programming is not easy. Okay? Put everything that has been created manually in version control. This is also something that I try to do. All of my projects are version control, from small programs that produce plots to note-taking and to sincere programming. And especially for the note-taking, which is done manually, I keep track of them in a distributed version control system. Because it just keeps me from committing stupid errors and then losing my notes. Which would be not nice. So this is just a safety precaution. Fourth set of rules, learn from your errors. But I think for scientists this is very near and dear. Top rule, don't repeat yourself. This is what also is sometimes referred to as the dry principle. Don't repeat R and Y yourself. Okay? Again, I personally have a 3 strikes you're out rule. If I see myself repeating the same task 2 or 3 times, I start to let it go. And this is what it's meant. And this also goes in line with your software development. If you see inside a function that, for example, you notice yourself copy and pasting, let's say 5 lines, and just inserting them 50 lines more below, and then just changing a couple of parameters. That's something to put into its own function, right there. Okay? Don't repeat yourself. Copy and paste is just the devil inside. Okay, every piece of data must have a single authoritative representation in the system. So here this refers actually to constants. I've seen a lot of programs where pi is actually defined more than 5 or 6 times. It's a natural constant, hello! I mean, pi doesn't change so much. And so if you have these kind of constants, this could refer to locations on the web, or, I don't know, some metadata of the input data, etc., etc. Define them once, and that's enough, right? If you copy and paste this, you are asking for trouble, okay? It's just, been there, done that, failed miserably. Modularize code rather than copy and pasting. So inside these courses, the maximum amount of abstraction that we actually reach is functions. Functions is and was the tool today to encapsulate functionality. With Python and also other languages, you can expand this notion to objects and classes in object-oriented languages. Whatever you take, functions or objects or singletons or whatever, just try to modularize the behavior as much as you can so that you can reuse functions. Especially in the context of test-driven development. Because what you don't want is, you don't want to happen to be in a situation where you test the function and then you copy and paste it and just change the parameters. Because then all the tests of basically your first implementation could have been run in the second as well. So modularize and really try to follow the single responsibility principle. This is something I do not have on the slides. This is a programming principle from the Agile development movement. Single responsibility means your function or your class should only have one responsibility, not more. Okay? So it starts out when, for example, I'm not talking this time. Rule 4C, reuse code instead of rewriting it. That's basically the same as I just said. Try to create, in terms of Python modules that you can reuse. In terms of other compiled languages, try to create libraries that you reuse. Because this is just for you. You just save time. And also for testing, you concentrate the effort of testing onto one specific behavior inside the library. And you don't scatter it around through the project or throughout many projects. Try to reuse code. Fifth part, mistakes happen, right? The guy just let it fall. I mean, now the wine is spilled. I mean, this just happens. As we said before, the precondition of defensive programming is that mistakes happen. So plan for them. Nothing catches all the mistakes. You have to be clear about this. So just try to practice defensive programming. Practice it, start in small projects, maybe expand it to larger ones, and you really make your own experiences. Right? And this simply increases productivity. Rule 5 extra, so Rule 5A and 5B. Add assumptions to your program. We've trained that today in the afternoon. And use an off-the-shelf unit testing library. This is actually the reason why I confused you with nose tests. Because I wanted to show you a library that actually helps you orchestrate and keep control of your tests. There are many more. And they are there in every language. Because the good thing is, I mean, today we only had a small function test, but in real life, you have a big project. You want to have somebody that helps you managing the setup, the execution, and reporting of the tests, right? Because, again, as I said this afternoon, rerunning unit tests after every change to the code and check for regressions. Here in this case, regression means that you broke something, right? By updating the code, you broke something. But I also know that testing is hard. It's not a piece of cake, and you all experienced this in my introduction. The overall problem for scientists typically that are exposed to test-driven development is typically they say, well, I don't know the result. This is research. If I would know the result, then I would have published it. This is not what test-driven development is all about. Test-driven development is about taking a program, pulling it apart into independent and individual pieces of functionality and testing them. If they work together in a way that you want it, is another thing. This is typically in software engineering called an integration test. But for you as a scientist, this is where the science starts to come in, right? Compared to experimental data, if you can, but be careful with this, because experimental data can include randomness, so your tests need to be prepared, or at best to analytical solutions of simple sub-problems, or maybe even old programs, legacy code, that you know for sure that works on a specific subset of your parameter space. So I also talked with a quantum field theorist at my old institute, and he always claims this. How am I supposed to test a big path integral? And I say, well, the only reason testing is only there for the units, for the subunits. If you cannot do that, it becomes very hard to test your software. Conversely, it becomes very hard to guarantee that it functions correctly. Yes. If all these tests actually fail, it's a good practice to actually inform your users. And please tell your users that you expect errors to happen, right? Because it's nothing, it's really frustrating. You get to know from a paper, hey, there's this cool tool you have to use, it's on GitHub and it's on version 15 and the last change was yesterday. So you think, wow, this is great. And then you download it, you run it, and it fails. And then you think, good, next to it. So this is really frustrating, right? If you expect errors from like the default test or something, communicate them. That's very important. Rule 5C, turn bugs into test cases. This is a good practice. If you collaborate with other people, they will for sure tell you what's not working right, I hope. And then what I also typically do, I turn them into test cases, okay, so that they are contained in my test suite. Test suite development we talked about this afternoon. This is a short summary why it's good and why it's good to adapt as a scientist. Always write the tests first, then the code. This improves the focus and encourages writing actual testable code and ensures tests actually get written, which is the sole purpose. And then refactor is basically the paradigm to follow. If you encounter problems that you cannot resolve, try to use a debugger. So I hope you know what a debugger is. A debugger is a program that helps you to step into your program while it's running and then stop it and check what intermediate values of variables are. If you have such a tool for your language, use it. And all languages have debuggers. Getproof. This is more, it's really close to most scientists. Optimize software, and this is coming back to what we discussed earlier. Optimize software only after it works correctly. Okay, so correct this first. You don't want to have a fast program that's wrong, because that doesn't help anybody, right? And so you want to have it giving you the right answer for some parameters that you expect some certain values for, and then you can sit down and actually improve the performance. And here, as a matter of fact, tests help you. This is why I also use unit tests. I mean, my task is to accelerate applications, but I want to have the tests as a side to know I didn't break functionality. Okay, very important. First, of course, use a profiler to identify bottlenecks. We discussed this really briefly in the afternoon. Many people just look at the code and say, I know what's going on. I have to do this for that. Most of the time they're wrong. Even people which are very long in the business are not following closely what compiler engineers do to their compilers. And so the landscape changes so fast, I always recommend, if you consider performance, measure. Okay? Never ever update your program just by thinking about the benefit of performance. Also, try to write the code in the highest level language possible and then go down. This is at first when I read this first time, I said, what? We're using C++, I mean, period. There's nothing I can change. Yes, you can. Of course, you can change something and learn to program C++ in a better way. The standard, for example, has evolved extensively. Or, what I did at some point, I started learning Python, in this case, to actually orchestrate better my software development cycle. So I then had some Python scripts that ran some statistics, or Python scripts that ran unit tests, etc., etc. This was well before I got to know builders. But anyway, I used a different language at higher level, and then when it was really necessary to actually have good performance, then go down and try a lower language. If your community only uses Fortran, then this is just the case. Then you cannot change it. Okay? I mean, we have to be realistic. Document. Document your design and purpose. Do not and never document mechanics. Everybody sees that you just created an array. Everybody sees that you wanted to access item 0 of the array. You don't have to tell anyone. But you have to tell everyone, why did you use an array? Does it have a specific size? What's the sense behind this? Maybe you had reason to limit your array to 128 elements. All that kind of stuff. Document why, not what. Okay? So it basically goes in line to what we said this morning about good commit messages. Alright? Yeah, this is a little bit more abstract now for those people that are into object-oriented programming. Try to document interfaces and reasons, not implementations. This is basically a special case of what I've said just a slide ago. Refactor code in reference to explain how it works. So this is also something that I typically encourage in my code. If I read through a function and I don't know what it's doing, I'm trying to refactor it. Trying to pull out parts which basically could go into a separate function, and then with this try to make the code more understandable. Embed the documentation for a piece of software in that software. Do not ever keep a log file somewhere that contains some outdated information of how the software would work. And then this is the last point, try to collaborate as much as you can. Biggest mistake, and I've seen this multiple times, is to keep your code for yourself. Because you're afraid to show other people that you cannot code Python as good as they do, or other weird arguments for not showing people. As I said before, programming is hard. I personally always encourage you, try to share your code, try to show the code, your code to other people if you have problems especially. Okay? Some extras here. This is more advanced for bigger projects. Use pre-merge code reviews. This is a technique for bigger teams that, for example, if a big release is coming up and pull requests are lining up, they get together and then review the changes that they want to put into the code base. And this is called a code review, and it's very good practice. Use pair programming when bringing someone new up to speed. So this is typically good when you have a new member of the team. Just take him for a day or two and just let him sit down next to you, and then you change over. This is very common technique in industry. There are a lot of tools, a lot of videos out there on YouTube, like big companies like SUSE, Google, Facebook, and all these kind of big names. They use pair programming. To be honest with you, I seldomly see scientists to do so. Different reasons for this. I think it's a shame, but still. Use an issue tracking tool. This is basically goes in line with using GitHub. GitHub actually offers you so that the users of your code can basically tell you, hey, I discovered a problem, can you please help me? This is what's called the issue, and it's on the right-hand side for every GitHub repository. And that brings me to my summary. I know this was quite a lot. I invite you to go to the paper and read through it, and this is basically the digest of it. If you can, use text-based interfaces. This means programming in text-based languages, which probably most of you do. Try to turn history into scripts and programs. Try to put everything in version control. And use test-driven development as much as you can. And all of these I can only say from my personal experience, has, especially the fourth point, has saved my butt many times so far. Okay? And with this I thank you for your attention, and I will open the floor. Are there any questions? Are there any comments?
What do you do with text-based interface in the editor?
No, but this is meant basically to prepare this point, put everything under version control. This means that if you can, you should put basically the source code of your intellectual results into text-based formats. So this would be LaTeX, Markdown, source code, like Java, whatever. Use that as much as possible. It goes back to the notion of the difference between version controlling a text file versus a binary file. Good. Yes.
So I learned that C++ is one of the lowest level languages, but I don't know, is there an intermediate level language? Because Python and MATLAB, that's already really high, right?
Yes, yeah, exactly. Python and MATLAB all work on the basis of C, and C++ is basically on the level of C. There's hardly an intermediate language. This is more like a slang in the community. Low-level languages are considered those where you have to keep track of the memory. And this applies to Python, C, and C++. Yes. All languages where basically the memory management, so meaning that you have to tell the compiler, I need 5 doubles, I need 24 integers. We don't have to do this and clean it up afterwards. This is called a high-level language. So this applies to Java, Python, Perl, many more. Okay? So yeah, as long as you can, try to stay out of the devil's den. and try to stay away of these native or low-level languages. But I also have to say that with the recent standards, especially of C and C++, things have improved immensely. So please have a look at these new standards. They help you get productive with C++. So, yeah. If not, then I thank you for your attention again. If you want to stay for the feedback review, you can. If not, I wish you a good way home. And thank you for attention throughout the day. And if you have any question, you can also always send me an email. Also, that's not a big deal.